SwayamPrabha. Digital India. Educated India.
Okay, welcome back to the lecture series of manufacturing automation. Let me remind you that in the last class we have discussed about the production and the throughput time. So, we have seen that the throughput is the time taken for an assembly to be completed, and also one fact that I would like to once again repeat, that in an assembly line, whether it is inline or the rotary one, each time its indexes will get one complete assembly. This you have to keep in mind. So, to compute the production rate, one has to know only the indexing cycle time. If you know the indexing cycle time, we will be knowing what is the production rate, because each time we know that it indexes, we get one complete assembly. Okay. Whereas, we said that the throughput time is the time taken for making a complete assembly. So, therefore, the throughput time will be equal to the production time and into the number of stations. So, number of stations will be immaterial while considering the production rate, whereas in considering the throughput time, we have to have the production rate into the number of machines, number of stations. In an example, we have seen that if we want to consider the actual average production rate, it will be very high if we do not consider the line breakage in case of automated assembly in the production flow line. And we have seen in that example that if we have 450 units per hour, ideally we could have got, then for one malfunction in 100 cycles, we are actually getting the percentage downtime as 86.3%, which is very high. Okay. Then in that example, we said that the station breakdown basically happens because of the improper tolerances or improper parts which go into the assembly and it stops the machine. So, the subsequent and the adjacent machines also get suffered. So, therefore, if we can improve the product quality, in that case we have taken in that example that suppose we have, instead of 1 out of 100, we have 1 out of 10,000 cycle malfunctioning, then it is improving drastically again, and the percentage downtime reduces to 18.4 from 86.3%. I am just reminding you, and therefore, the production efficiency goes up to 81.6%. Okay. So, through this example I wanted to show that the machine breakdown has to be considered while discussing or while taking care of the production flow line for the assembly. Next, we started discussing the vibratory bowl feeder, and we said that for small engineering parts which are majority in the assembly process, feeding the parts to the machine is very important aspect, very important phenomena, and therefore, the feeders which actually do that, those have to be considered, those have to be designed in a proper way. Here there is one minor point that I would like to mention right away here, that parts have to be fed to the machine, not only fed to the machine, but the parts have to be fed in a right orientation. For example, what I mean to say is that suppose we have a part which has to go like this. Okay. If the part is coming like this, it has to be reoriented, because it will not, if it goes like this and comes to the machine, again the machine jams. It cannot go in this orientation to the machine. It is desired orientation is only this, for example. So, if the part is coming like that, either it has to be rejected from the track and let it go again right when it comes in the right orientation, or it has to be reoriented. So, therefore, the responsibility of the ball feeder is very serious, in the sense that it will not only feed the parts, it will feed also, it has to feed also in the right orientation. Vibratory ball feeder is one of the most important and one of the most versatile ball feeders for small engineering parts. And I told you already in the last class that this consists of a bowl and a base. The bowl is connected to the base with the leaf springs, okay, and in the bowl there is, in the base of the bowl there is a electromagnet. That electromagnet imparts the vibration to the bowl, and inside the bowl there is a track which is inclined to the horizontal, and this is spirally going from the base of the bowl to the outlet. So, when the vibration will be imparted to the bowl, each part located on the track will be moving in a short, straight, almost straight direction, which will be inclined to the track with an angle more than the angle of inclination of the track. What is it? I will explain it to you. Now, first of all, let us see that why these parts have to ride on the track of the vibratory ball feeder. When the electromagnet imparts the vibration, it will impart two types of vibration. One is the vibration like this, that is a vertical axis along about its vertical axis, okay, and this is a linear vertical vibration, and there is another vibration which will be torsional vibration like this. So, as a coupling these two, what happens is as the part is going like this, also it is getting a torsion. So, it will be moving like that. That means, this vibration will allow the part to leave the track, and as soon as it is leaving, that torsional vibration that will help the part to move ahead. So, this will be overall, there will be a small straight line vibration of the part, each part which is located in the on the track of the vibratory ball feeder, and this straight line will be inclined to the track at an angle more than the angle of inclination of the track. Okay. All right. Now, let us see what is the mechanics of vibratory conveying. Let us take an example of a small part which is located at the on the track of the vibratory ball feeder. This is the track which is inclined to the horizontal at an angle of theta. Okay. Now, this is when it is moving, the MP, which is the part weight, let us say, okay, and mass of the part, and this is the vibration, overall resulting vibration that you will be getting, which is MP A0 and the omega square. MP is the mass of the part, okay. A0 is the acceleration and the omega is the angular velocity. So, for sliding up the track to occur, if it has to go like that, this MP A0 omega square will have the MP A0 omega square cos of the psi in this direction, in the direction along this F. The F is the frictional force, N is the normal force. Because of this, there is a friction force of F, okay, and mu S is the static coefficient of friction between the part and the track. Okay. So, this in the direction of the normal force, MP A0 omega square has a component of MP A0 omega square and the sin psi. Okay. So, this in the n direction, that is a normal direction, the component which will be coming here is the MP A0 omega square and the sin psi, and in this direction it is the cos psi. We have the MPG here. So, MPG will have two components, okay. One is in the direction of n and another is in the direction of the f, all right. So, this will be MPG sin theta and this will be MPG cos theta, all right. Now, for sliding up the track, here in this direction, well, this component, this is MPG sin theta and this component is MPG cos theta. So, therefore, in this direction we have the MP A0 omega square cos psi, this component, and this component has to be then more, because it has to go up the slide up the track, has to be more than MP, this force which is MP g and the sine theta plus F. F is the friction force because of the normal force acting here. All right. So, for sliding up the track we have to have this condition satisfied, where this F is the friction force which is mu s, which is the static coefficient of friction between the part and the track, as I said, into the normal force here. Okay. So, the friction force here is the F mu s into n, which is normal force. This is equal to mu s, okay, mu s into n. We can find out this is this force minus this force. So, which is MPg cos theta is this component minus MP A0 omega square and the sin psi. So, this component minus this component is that n. So, we are putting this value here, and mu s into n, this will give you the F, which is the friction force. That means, here if you put in the equation 1, here if you put the value of the F, which is this, in the equation 2, you will get the equation as MP A0 omega square cos psi. This has to be more than the MP you are taking and putting the value of the F, this value, and you are getting this equation. Now, this can be simplified, and this is simplified in this way. You get the common of A0 omega square, this will be into cos psi plus mu s sin psi, which will be more than g and the sin theta plus mu s cos theta, and overall what we are getting is that A0 omega square divided by g, this is more than mu s cos theta plus sin theta divided by cos psi plus mu s sin phi, meaning that this is the condition that has to be satisfied for the part to slide up the track. Similarly, it can be shown that for backward sliding, that means whether the part is going up or going down. For going up, this is the condition that has to be satisfied, and you can show that when the part is going down, what will be the condition of these forces? It will be reverse, and you can say that A0 omega square divided by g, this has to be more than mu s cos theta minus sin theta divided by cos psi minus mu s sin psi. So, these are the two conditions which are coming here. These conditions will actually have, these conditions have to be satisfied either for the work to, I mean for the part to go up the track or for the part to slide down the track. In the sense, why it is so important? Because if you have this equation satisfied, in that case you can make sure that the part will go up, because the vibration may not be sufficient, amplitude or the frequency is of the vibration may not be enough for the part to go up. So, you have to always see that these conditions are satisfied, particularly this condition, because we want the part to go up, and in case this is satisfying, that means you know that the part will not go up, it will go down. The operating condition of vibratory conveyor, including the bowl feeder, may be expressed in terms of dimensionless normal track acceleration. This is normal track acceleration, which is a convenient way of expressing the operating condition. And let us say the normal track acceleration is an by gn. Okay. Now, this an by gn can be found out because the an, which is the normal track acceleration, this is given by an into omega square, okay, and this is equal to A0 omega square and the sin psi, all right, and the gn, which is the normal acceleration due to gravity, this is equal to g and the cos theta. G is the acceleration due to gravity. This A0, this is the acceleration of the part on the track, okay, linear acceleration, and the g, which is the acceleration due to gravity, this is, we know that this is 9.81 meter per second square, and therefore, if we are substituting this value an by gn that you will be getting here in the equation 3 this equation, okay, then we will be getting that a n by g n is equal to a 0 omega square sin psi divided by g cos theta. You can find out from here, okay, that in this equation we are substituting the a n by g n, and a n by g n will be a 0 omega square sin psi divided by g cos theta, okay, and that will give you the a n by g n is equal to a 0 omega square sin psi divided by g cos theta. Now, from here you can find out that the normal the dimensionless normal track acceleration, this a n by g n, this has to be more than the mu s plus tan theta divided by cot psi plus mu s. Okay. So, this where you are getting from, you can see that earlier equations, okay, and if we equalize this equation, equalize this one, all right, with this, then you will get this for sliding up forward. And similarly, if we are taking this equation and substituting with this, you will get the, or substituting with the equation when the part goes backward, then we will be getting the equation or the condition for the backward sliding. So, this is more convenient to use because this is the component which is actually which dictates the operating condition of the vibratory ball feeder. This is the normal track acceleration and this is the dimensionless, therefore, it is more convenient. So, therefore, this is important for us that for forward sliding we have to have this condition satisfied. In that case, we know that the parts are properly going up the track. Now, here one condition you can see that apart from the mu s, which is the static coefficient of friction between the track and the part, we have two more angles which are important. One is the track inclination angle, which is the theta, and another is the vibration angle. Okay. Now, if we go back to the to this, vibration angle is one where this MP A0 omega square, because of the vibration total inertia force, this will be making an angle with the parallel to the track angle of the psi, which we are calling as the vibration angle. Okay. And the track inclination angle is theta, which the track is making with the horizontal. So, initially when I said that because of the two vibrations, that is the linear vibration, okay, and the torsional vibration, the part will move in a short straight line at an angle more than the angle of inclination of the track, meaning that this is the angle which is apart from the theta they are getting. That means, this angle it is moving like this, okay, along this direction. So, this angle is more than the track inclination angle. So, therefore, in this we have apart from the mu s, which is the static coefficient of friction, we have the track inclination angle and the vibration angle, which are important to find out that whether the normal track acceleration is proper. Okay. So, these angles are actually depending how these angles are determined or how these angles are defined, that also depends on us, because what happens is the track inclination we can incline the track, that is a design, okay, and the psi, which is the vibration angle, that depends on the on what, on the electromagnet which we have here, plus the suspension springs. Okay. In the suspension spring, the spring constant and the angle, these two factors will define how the vibration will be imparted, and these vibrations are actually like this, that is the torsional vibration about its vertical axis coupled with a linear vertical vibration. This is the linear vertical vibration and this is the torsional vibration. So, this will depend on once again the suspension springs and the electromagnet. So, therefore, we can actually decide what will be the angle psi, which is the vibration angle, and this angle is the track inclination angle, once again we can decide. So, by deciding the mu s, track inclination angle and the vibration angle, we can actually satisfy that the normal track inclination, normal track acceleration should be more than this equation, than this factor. Then only the parts will go along the track up, that is at the outlet of the vibratory bowl feeder. Now, for values of, for example, mu s is equal to 0.8, let us take a practical value, suppose it is 0.8 and we have the track inclination angle as 3 degree and the vibration angle as 30 degree. In that case, An by Gn, which is a normal track acceleration, must be more than 0.34 for forward sliding. We are getting it from here, as you understand. Okay. So, you put the values of mu s is equal to 0.8, mu s is equal to 0.8, theta is equal to 3 degree here and psi is equal to 30 degree. You will get the An by Gn, which should be more than 0.34 for the forward sliding, and An by Gn more than 0.8 according to that equation for the backward sliding. This is just an example, that if it is 0.8 static coefficient of friction, 3 degree inclination, so then it has to be more than 0.34. This I am mentioning because while designing the vibratory bowl feeder, you have to take into consideration these factors. Okay. Now, once we have these two, that means mu s plus tan theta divided by cot psi plus mu s, this is for the forward movement and this one is for the backward movement. So, if we equalize them, okay, this will be the limiting condition for forward conveying to occur. What does it mean? That this is the condition at which the part will just start going forward, it is in the limiting position. So, from here we can find out that if we solve this equation, you will get the mu s square is equal to tan theta plus cot psi. So, this is the condition that you are getting. So, from here the limiting condition is the tan psi is more than tan theta divided by mu s. As I said that this is equal to, because this is the limiting condition. That means, at this condition the part is neither moving forward nor moving backward, it is in the initial position, okay, in the position just ready to move. So, if it is more than that, that means the part will start moving forward, that is the one thing. Now, this can be simplified, that if the track inclination angle is small, so we can consider the tan theta is equal to theta, and then we can say simplified way that the tan psi, which is the tan of the vibration angle, this has to be more than theta by mu s. So, this is the condition that has to be satisfied once again for parts to move forward. So, this is much more simplified, because you can see that here we have the theta and we have the mu s, which are in our hands, in the sense that how much track inclination angle we are giving, that is the design criteria, and what kind of smoothness we are giving to the track and what kind of parts we are having, depending on that we will be getting the static coefficient of friction. So, once we have the theta and the mu s, we can take the ratio and we can find out that what is the value of the vibration angle. Depending on that, we can select the suspension springs, the angle of the suspension springs, and the spring constant. Okay. These are the suspension springs at which angle you are actually attaching the ball with the base, and what is the spring constant, that is material, okay, and what is the electromagnet, of course, that will depend, that will actually be selected based on the psi that you would like to have for the forward movement. Now, you mind one thing, that the parts are of different materials. For example, there are aluminum parts, there could be steel parts, there could be parts with a rougher surface or with smooth surface. So, that will actually determine your mu s, which will be the static coefficient of friction between the parts and the track. So, depending on that, you will actually get the psi, which is the vibration angle, and you can design accordingly the electromagnet, select the electromagnet and design the suspension springs and the angle of the suspension springs. Once again, here it is the design aspects that we are considering. In the design aspect, the basic thing that you have to take into consideration is the parts should be moving along the tracks, along the track, inclined track, which is inside the ball, and the parts have to come out of the ball. okay, because these parts from here they will actually go to the machine for assembly. This is small engineering parts. So, if you see actually a bowl feeder in practice, you will see as if the whole ball is moving, whole track is moving. It seems that as if the track is moving. It is actually not the case. On the track, the parts are actually moving and the track is stationary. But if you actually see this, it's a very good design. You will see that as if the ball is moving. Okay, this is a concept, but actually the parts are moving along this. So, as now you know that for parts to move along the track, ultimately what we need is this condition to satisfy. Okay. That means accordingly you have to design your track inclination angle, accordingly you have to design the springs, accordingly you have to select the electromagnet. The rest of it I will discuss in my next class. Thank you very much.